All right, so first we're going to talk about a critical point. A critical point is where the derivative is 0 or undefined. So where the derivative is 0 or undefined. And if your derivative is 0, that's where you end up with a horizontal tangent line. So like this, or you can draw in a tangent line that's horizontal. So that's where you have a critical point. This is where these critical points are where you have the potential for relative maximums and minimums. I say the potential for them because you might have them, but you might not. And I'm going to draw a few pictures to show you. Okay. So say you have a parabola, something like this. Here's where you would have a critical point. There's a horizontal tangent line there. Or if the parabola was upside down, this would be a critical point. And so you can see you end up with a relative minimum here and a relative maximum there. But say you have something like a cubic graph. You get a horizontal tangent line there. That's a critical point, but you don't get a relative maximum or minimum, but it's still a critical point. Foreshadowing, do you remember inflection points? Inflection points are only inflection points if there's a change in concavity. We're going to talk about that more next unit, but critical points are critical points no matter what. This is still a critical point. And then this would also be a critical point right here. You get the derivative being undefined there because you have that sharp edge. The slopes from each side don't match up, but that's still a critical point, and it's where you end up with a relative minimum. Right, so if your function is increasing, your derivative is positive. If your function is decreasing, your derivative is negative. And I'm going to draw a little picture of each of those to illustrate. So here's a function that's increasing. If I start drawing in tangent lines, like here's a tangent line, here's a tangent line, do you see how they all have positive slopes? They're all increasing. And here's a function that's decreasing. If I draw in tangent lines, do you see how they're all going downwards? So that's why that's true. And I usually put it in a chart. Here's F prime, increasing positive, decreasing negative. And we're going to add on to that chart as you learn more stuff and we get into the second derivative. But for right now, isn't that chart life-saving? Like all that information right in one spot? But that's just the beginning of it. So increasing positive, decreasing negative. All right, so what we're going to do for these, we're going to state the critical points, label them as a relative maximum or minimum, or neither. I guess I should have put neither on there too. And then sketch a graph of the derivative. I like doing this with 2 different colors. If you have like 2 different colored highlighters, you can do that to illustrate this. Or if not, that's cool too. None of you reached for your bag to get out a highlighter, so I'm going to take it that you don't care, but I'm going to color code mine because that's the kind of person that I am, all right? So where is our critical point for this first graph? Yeah, 0, good. And we only need the x value. You're very thorough with 0, 0. We only need the x value. So you have a horizontal tangent line there. And that is where we have a relative minimum. So we have a relative minimum at x equals 0. And you can draw yourself a graph over here. We're going to sketch the derivatives. It's not going to be like super perfect. The only points you're going to plot specifically are the critical points. And it is at 0. So you'll have a point at the origin. So I'm going to do my decreasing parts green and my increasing parts pink. Decreasing means negative, increasing means positive. So when I sketch this derivative, it should be below the x-axis and then above the x-axis. And I call it below sea level and above sea level. It's silly, just helps everybody remember. I did have someone on a test once write above sea level. Don't do that on the AP exam though. Okay, and they will be like, what on earth are you talking about? But it should be below and then above and go through that point. And that's it. I'm going to do the easiest example first, so they're going to get more complicated. All right, this one has 2 critical points. Where is one of them? Good, -2, we have a horizontal tangent line. Where else? 1. So when you go to do your graph, Those are the only 2 points that we're going to plot specifically, -2 and 1. The reason they're on the x-axis is those are zeros. That's where you have a zero slope. When you graph a derivative, you're making a visual representation of the slope. It's kind of interesting. And so we have a relative maximum at x equals -2 and a relative minimum at x equals 1. And so again, I'm going to color code. We are increasing, then decreasing, then increasing, which means our derivative should be positive and then negative and then positive. So we want to be above sea level, below sea level, and then above sea level and connect to these points. So it's above, below, above. Yes, and I'm going to bring that up at the end, so hold on to that. All right, so go ahead and flip over. This one has 3 critical points. Can you guys tell me one of them? 1. Good. 3. And then one more. -2. Good. Nice. So when you go to plot your points on your derivative graph, those are the only ones you're going to plot specifically. You're going to have, what do we say, -2, 1, and 3. So this graph is increasing, still increasing, decreasing, and then increasing. So we want to be above, above, below, above. So watch. We're going to be above the x-axis, connect to this point, stay above. And then after we connect to the next point, next critical point, we'll go below and then above. Oh, and I didn't list out the critical points. All right. At -2, we have neither a relative maximum or relative minimum. So neither at x equals -2, but it's still a critical point. Still counts as a critical point. And then we have relative maximum at x equals 1, and then relative minimum at x equals 3. All right, next we've got the absolute value graph. Where is our critical point? 0. Now, you cannot put that point over here, though. It's not a horizontal tangent line. That's where a derivative is undefined. So we're not going to get a point at 0 over here. So you're like, well, there's nothing to connect to. Okay, well, hold on. We are decreasing and then increasing. Now, because these are linear, we can figure out what the slope is exactly. Like on this one, I was just sort of estimating. It was like above and below, but here we can get it exactly. What's the slope of this green segment? -1, and then this segment 1. So we're going to have a line at -1 until we get to the critical point, and then +1. And do you remember when I brought those up during the limits and I was like, hey, we're going to talk about this later? It's the derivative graph of absolute value is what those are. Yeah, it's written out absolute value of x over x is how that looks. And that is still a critical point. So I'm going to say relative minimum at x equals. Because it is still a critical point. The derivative is undefined there. It's still a critical point. All right, then we've got exponential. What's kind of interesting about this one is what? Like if we were to list out the critical points, where are they? Yeah, there aren't any, right? There's no critical points. So when we go to graph here, there's nothing we can put on there. And the graph is increasing all of the time. So we want our derivative to be above sea level all of the time. Well, where does it go? All right, if I were to start drawing in tangent lines, they would have really small slopes at the beginning. And then as we go on, they would get steeper and steeper and steeper. Do you see what I'm saying there? Like if you draw them in, it's going to be really small and then get bigger and bigger and bigger. So when you draw this, it's going to start out really small and then get bigger and bigger and bigger. And this is just so cool. It geeks me out because the derivative of exponential is just like it's itself, which is cool. You what? Yeah, I know. I love that one. Is e to the x. Thank you, sir. All right, what is this the graph of? I know you're like existential crisis, right? It is sine. Sine starts at the origin. Cosine starts at 1. Okay, so this is sine. Critical points, you're going to have an infinite number of them. Let me go ahead and put those on the grid over here. So when you have an infinite number of them, you're going to start at the first one. And then do you guys remember that plus n, however many, like, because it's going to cyclic, you're going to keep on getting them. All right, so we're going to have a relative maximum, or I guess plural, relative maximums at, all right, and then the first maximum is at pi over 2. And then we're going to say plus 2 pi n. What that means is every 2 pi, you get another one, cyclic. So every time around the unit circle, you're going to get another maximum. And then the same thing with the minimums. We're going to have a relative minimum at 3 pi over 2, so where the first minimum is. And then plus 2 pi n. So every time you go around the unit circle, you get another one. Oh, I'm sorry. I should have put an x equals. Thank you. That's not something you would like, I guess, necessarily lose points over, but it should technically be. All right, so I color coded. We want to be below and then above and then below. So let me see where I started here. So we're going to be below and then above and then below. And then it's going to keep on doing that, you know, forever and ever. So the derivative of sine is cosine. And then here's what you kind of brought up, Jenna, a little bit ago. What happens to the degree of a polynomial every time you take a derivative? Let me flip back. This one was a parabola, its derivative was linear. This one was cubic, its derivative was a parabola. What's happening to the degree every time? Decreases by 1. If this won't unfreeze, I'm gonna have to redo the video. Oh, crisis averted. Okay, decreases by 1. And I'm gonna put the order on here. If you have a cubic function and you do the derivative, it's gonna become quadratic. The derivative of a quadratic is linear. What would be the derivative of linear? Good, constant. And the derivative of a constant is just 0. And then the derivative of 0 would be 0. Here's what I'm going to do because I'm nervous this is going to freeze. Because I was going to do like a 2-minute brain break here anyway. I'm going to stop the video and let this video download so I don't lose this at least. And then I'll reopen it for the second half of the notes. Okay.